A robot does not inherently understand the physical world. Its internal controller only receives data from its own hardware, specifically the angular position and rotational velocity of its motors. This internal frame of reference is known as joint space. But the tasks a robot actually needs to perform, an environment defined by x, y, and z coordinates known as Cartesian space. To bridge the gap between internal motor angles and external reality, controllers rely on the Homogeneous Transformation matrix, a mathematical engine used to map static spatial geometry. When that geometry starts moving, the system relies on a secondary engine, the Jacobian matrix, to map dynamic motion and physical force. Without these two linear algebraic constructs, a robot is blind hardware spinning in a void. Together, they form the architectural foundation of every autonomous controller in existence. We can observe how this geometry is built from first principles by mapping a specific point on a two-dimensional plane. We start with a pink fixed frame, representing the room, and a white moving frame, representing the robot's base, perfectly aligned at the origin. The first type of movement is pure translation. The white moving frame shifts along a straight line, driven by a linear displacement vector. The second type of movement is pure rotation. The moving frame pivots counterclockwise around its new origin by a specific angle, theta. To find the new coordinates of a point in the fixed frame, traditional algebra requires two distinct operations. You multiply the moving frame's coordinates by a rotation matrix, and then you add the linear displacement vector. This two-step process works fine for a single movement, but industrial robots have 6 or 7 joints operating in a continuous chain. Managing alternating sequences of matrix multiplication and vector addition across multiple links immediately creates a computational bottleneck. The solution is the Homogeneous Transformation matrix. By appending a 1 to the end of our coordinate vectors, we can package both the rotation matrix and the displacement vector into a single, unified grid. The bottom row absorbs the extra variable, creating a 3x3 mathematical structure known as the Special Euclidean Group, or SE2, which is used for planar robotic cases. For complex spatial reasoning in 3 dimensions, the exact same logic applies, scaling up to an SE3 group represented by a 4x4 matrix. Packaging rotation and translation into one matrix eliminates the addition step entirely. Now, to map the exact Cartesian location of a robot's tip, engineers can simply multiply the matrices of each individual joint sequentially down the chain. The Homogeneous Transformation matrix takes the messy physical geometry of pivoting hardware and converts it into a clean, highly scalable linear algebraic pipeline. That scalability is tested in complex environments where independent agents share a physical workspace. If 2 mobile robots are operating in the same room, the system has to guarantee they won't collide. The central controller tracks Robot A's end effector relative to a fixed origin point in the room, utilizing a specific transformation matrix. Simultaneously, it tracks Robot B's end effector relative to that exact same fixed origin. Knowing their positions relative to the room isn't enough. The critical safety requirement is establishing the exact relative distance between Robot A and Robot B. We define this algebraically. Transform A is equal to transform B, multiplied by the unknown relative transformation matrix between the 2 robots.
To solve for that relative transform, we rearrange the equation. We multiply transform A by the inverse of transform B. Calculating this inverse matrix isolates the exact spatial coordinates we need. The top right column of the resulting matrix yields the precise relative displacement values, delta x and delta y. This drives the system's collision logic. The controller monitors those specific displacement values. If they approach 0, the physical end effectors are about to overlap. By utilizing inverse transformations, independent agents calculate precise spatial threats relative to one another, solving physical navigation entirely through matrix algebra. Establishing static position is only half the problem. A controller also has to calculate exactly how fast the end effector is moving. We start with the expanded forward kinematics, the equations determining physical displacement for a standard 2-link robot, based on its link lengths and joint angles. Mapping speed requires calculus. By applying a time derivative across these spatial equations, we convert the static joint angles into angular velocities. Next, we execute a mathematical grouping process, factoring the angular velocity variables of the internal motors out into their own distinct column vector. What remains is a newly isolated 2x2 matrix of coefficients. This is the Jacobian matrix. The values inside the Jacobian are not static. Because they are derived from the current joint angles, the matrix recalculates constantly, reflecting the robot's specific geometric configuration at any exact millisecond. There is a strict engineering rule for this equation. To yield accurate physical speeds, the incoming motor velocities must always be calculated in radians per second, never degrees. The Jacobian matrix operates as the ultimate dynamic bridge, allowing the controller to instantly translate internal motor RPMs into external Cartesian tip speed. We can pivot away from motion to examine static equilibrium. When a robot is standing perfectly still, holding a heavy object, the kinematics equations still govern its behavior. A heavy payload exerts a downward gravitational force and a rotational moment directly on the robot's end effector. To maintain a perfectly stationary state, the robot's internal motors must generate equal and opposite torques to fight that payload. To find exactly how much torque is required, we use the torque equilibrium equation. This utilizes a manipulated version of the Jacobian matrix, explicitly applying a matrix transpose. Transposing the Jacobian reverses the math pipeline. Instead of mapping joint speeds forward to tip velocities, it maps external Cartesian forces backward into internal joint space, outputting the exact torques required at each motor. This specific matrix operation directly dictates the physical hardware design of the robot. By calculating the transposed Jacobian against the maximum expected payload, engineers determine exactly how powerful the internal motors must be before the machine is even built. Sensors and actuators are blind hardware without a central mathematical interpreter. The homogeneous transformation matrix sits at the controller's core, filtering geometric data to continually rebuild a precise 3D spatial model. Beside it, the Jacobian matrix processes dynamic intent, translating forces into outgoing actuator commands. In modern industrial applications, these matrices are not solved once. They are recalculated continuously at incredibly high frequencies to maintain perfectly smooth, high-speed operation. Linear algebra is the computational heartbeat of robotics, translating raw motor angles into the precise, autonomous manipulation of the physical world.